So if you just pause a dash cam video of a car going like 60 miles an hour, how fast is the car actually moving in that exact frozen frame?
Well, it isn't moving at all, right? I mean, time has stopped, so distance has stopped. The speed in that singular frozen image is just zero.
Right. But if the speed in that exact instant is zero,
Yeah.
and the whole drive is just, a continuous series of those frozen instants,
Uh,
then how is the car moving at all? Like, we know it's going 60 miles an hour. We can feel the momentum.
yeah, absolutely.
But when we try to look at what's happening right now at like one specific mathematical instant, the movement just completely vanishes.
Yeah, you've basically just stumbled into this arithmetic black hole that broke mathematics for centuries.
Wow, really? Centuries.
Oh, totally. You are looking at the fundamental contradiction of continuous change.
Well, for you listening right now, this paradox is our mission today. We are taking a deep dive into the very architecture of reality.
It's a big one.
It is. We're demystifying what we can really only describe as the final boss concepts of mathematics. Limits, derivatives, and the notoriously intimidating Epsilon-Delta proofs.
Yeah, those terms carry an immense amount of baggage.
Sure.
I mean, for anyone who has ever sat in a calculus classroom, they just sound like an impenetrable avalanche of complicated Greek symbols.
They usually look like some ancient alchemy text, honestly. But based on the stack of sources we're pulling from today, we're going to look past all that intimidating notation.
Right, getting past the symbols.
Exactly. We are going to explore how these massive, world-altering mathematical concepts actually stem from a very simple, everyday feeling of human discomfort.
Yeah, the discomfort of realizing that our everyday language just entirely fails to describe the physical universe.
Right.
It really boils down to this profoundly human question,
Yeah.
What does it actually mean to approach something?
Because we use the word close constantly, right? Like, if I tell you I'm close to the grocery store, that ambiguity is socially functional.
Yeah, I'm not going to ask you for your exact GPS coordinates down to the millimeter.
Right, that would be weird. So we survive on this socially acceptable ambiguity.
We do, but, mathematics cannot operate on feelings or vibes.
Definitely not.
When we build a suspension bridge or calculate the orbital insertion of a communication satellite, the word close becomes a catastrophic liability.
Because a millimeter of ambiguity on a launch pad translates to, what, missing a whole celestial body entirely by the time you're in deep space?
Exactly. You miss the planet completely.
Yeah.
So we need a system that removes the ambiguity.
Right, but before we get to the really rigorous proofs, we have to let's build a mental staircase together for this deep dive.
I like that, a mental staircase.
Yeah, so we're starting with human intuition, exploring why standard math fails us, and then we'll arrive at the bulletproof blueprint for understanding motion.
Sounds like a plan.
So let's linger on this arithmetic black hole for a second. Why was the concept of a limit even invented in the first place?
Well, to understand the invention of the limit, we really have to look closely at the zero problem.
The zero problem. Okay.
Yeah, as we established with your dash cam analogy earlier, when we observe reality, we constantly want to know the value of something at a perfect singular instant.
Right. We want to pinpoint exactness in a universe that's just constantly moving.
Exactly. You want to know your exact speed at precisely 12.14 in 32
It's
seconds.
not a range of time. I want that exact slice of reality.
But an instant, by its very nature, has no duration.
Right.
It means a time difference of exactly zero.
Yeah, 0 seconds have passed in a frozen frame.
And basic arithmetic, addition, subtraction, multiplication, division, that stuff has governed human trade and architecture for millennia.
Sure.
Yet, the moment we try to freeze time and use zero, arithmetic just throws its hands up in the air.
Because division is fundamentally a process of finding out how many times one quantity fits into another, right?
Exactly. It's grouping.
Like, if you have 10 apples and you divide them by 2, you're just asking how many groups of 2 fit into 10.
Right, which is 5 groups. It's a very logical physical reality.
Right.
But if you want to find the speed of a car at an exact instant, you are asking how much distance was covered in 0 seconds.
You're dividing by 0.
Yeah, you are asking arithmetic, how many times does nothing fit into something?
And the answer isn't 0, is it? The answer is just nonsense.
It's total nonsense. It completely shatters the foundational logic of the system.
Wow.
The mathematical universe essentially throws a fatal error code. I mean, you cannot build a predictive model of a moving universe if your primary tool crashes every time you ask it what is happening right now.
So we have this profound everyday need to know what is happening in the current instant, but our foundational tool just straight up forbids us from calculating it?
Yes.
So how do we bypass that prohibition?
Well, we stop trying to hit the target directly. We invent the limit.
Okay, the limit.
Yeah, the limit is this ingenious workaround that fundamentally alters how we analyze numbers. It basically represents how a quantity behaves as it gets infinitely close to a specific value without actually having to perfectly hit that exact point.
Oh, I see. So if the destination is this arithmetic black hole, where dividing by 0 destroys our entire calculation, we just orbit as close to the black hole as possible without actually touching it.
That's a great way to put it. We take all our measurements from the orbit.
Okay, so we're not ignoring the destination.
No, not at all. We isolate it, we acknowledge it's an arithmetic singularity, and we just map the gravitational pull around it, so to speak.
The sources we're referencing provide some really fantastic visual analogies for how this maps to our physical perception.
Yeah, the roadmap example is great.
Right, like if you look at a map of a country, a major highway is represented as this thin, perfectly straight, one-dimensional line.
Exactly. It has length, but practically no width.
On paper, the road is a highly simplified concept.
But when you actually drive onto that highway, when you physically approach it, it's not aligned at all.
No, it's a massive expanse of asphalt. It's like 60 feet wide with lanes and shoulders and grooves and all this texture.
Right. The closer you get, the more the reality of the object reveals itself to you.
So the limit is basically mathematics formalization of zooming in.
Exactly. Instead of plugging in the exact 0 that crashes the equation, we ask the equation a totally different question.
What are we asking it?
We ask, what are you doing as we tighten our orbit? We look at the behavior of the output as the input shrinks down to these microscopic levels.
So we're basically interrogating the math. Like, I know you're going to crash if I plug in a 0 here, so I'm not going to.
Right. You withhold the 0.
But if I plug in 0.1, and then 0.01, and then 0.0001, what number are you trying to become before you break?
Yes. What number are you trying to become? That captures the underlying philosophy perfectly.
It's kind of a sneaky workaround.
It really is.
Yeah.
This simple shift in perspective, analyzing the approach rather than demanding the destination, is the skeleton key that unlocks the entirety of calculus.
Okay, so we've established that limits allow us to look at an exact neighborhood without triggering the whole division by 0 self-destruct sequence.
Right.
But how do we take that observational tool and use it to measure actual motion? I feel like this brings us to the second boss on our mental staircase.
Taming the instant. The derivative.
The derivative.
Yeah, the derivative is simply the limit applied specifically to motion and change. It measures instantaneous rate of change.
Instantaneous rate of change. I mean, that feels like a linguistic paradox.
How do you mean?
Well, change by definition requires time, right? You need a before and an after state to observe a change.
Sure.
But instantaneous implies no time has passed at all. So how can you measure a change in a window of literally no time?
And that paradox is exactly what the derivative solves. Let's return to the dash cam and the car moving at 60 miles an hour.
Okay, back in the car.
If you travel 60 miles in exactly 1 hour, your average speed is 60 miles per hour.
Simple enough, distance divided by time.
But that is just your average speed over a massive chunk of time.
Right.
During that hour, your speed fluctuated wildly. You stopped at red lights, you accelerated onto freeway ramps, maybe you slowed down for a passing truck.
Yeah, the 60 miles per hour is a huge simplification of a highly dynamic event. My speedometer was a constantly moving needle.
Exactly. And if we want to know what that needle pointed to at exactly 12.14 and 32 seconds, we hit the frozen frame problem again.
Because time is 0, distance is 0, and division fails, we can't check the speedometer on the frozen frame.
But because we have the limit, we don't actually freeze the frame completely.
Oh, right. We use the orbit.
Yes. The derivative solution dictates that instead of pausing the video, we play it at the most microscopic speed possible. We shrink the time interval so it gets infinitely close to 0.
So we look at like a tenth of a second, then a hundredth, then a millionth of a second.
Exactly. We take your physical position at 12.14.32 and your position a millionth of a second later. We find the microscopic fraction of a millimeter you traveled in that fraction of a microsecond, and we divide them.
Oh, wow. And we use the limit to track what number that calculation is approaching as the time gap shrinks toward absolute nothingness.
You've got it. We never actually arrive at the frozen frame. We just hover just a hair above, completely paused.
And the math reveals the hidden speed at that invisible threshold. That's honestly brilliant.
It really is. By doing this, We can define the exact steepness or the speed or the rate of change at one singular point on a curve.
I remember learning about slopes in early algebra, the classic rise over run of a straight line on a graph.
Yeah, rise over run, a classic.
For a straight line, the slope is a fixed rule. If it goes up 2 units for every 1 unit across, it just does that forever.
True. Straight lines are mathematically obedient, but the natural world is entirely disobedient.
Right, nothing in nature moves in perfect straight lines indefinitely.
No, reality is composed of continuous, shifting curves.
And the slope of a curve is constantly mutating. Like at the bottom of a bowl, the slope is flat, but as you move up the sides, it becomes steeper and steeper.
Exactly. And before the derivative, mathematicians had no reliable mechanism to calculate the exact steepness of a curve at one isolated coordinate.
Because you need 2 points for a line.
Right. To find a slope using traditional algebra, you require 2 distinct coordinates to draw a connecting line, a second line.
So if you only have 1 coordinate, you are conceptually paralyzed.
Yes. The derivative shatters that paralysis by bringing a second, imaginary point infinitely close to the first point using the limit.
And the line connecting them becomes a tangent line, just brushing the curve perfectly at that single point.
Precisely.
The real-world implications of that are staggering, honestly. Because the curve doesn't just represent physical speed, does it?
Not at all. It represents anything in our universe that continuously shifts.
Like what? Give me some examples.
Well, the curve could be a graph of the temperature in a chemical reactor over time. The derivative reveals the exact rate the mixture is heating up at precisely 2.00 p.m.
Okay.
Or it could be voltage in an electrical circuit, or even the population density of a bacterial colony expanding at a specific millisecond.
Wow, so it's basically the universal speedometer for anything in reality that changes.
That's a perfect analogy.
Yeah.
As long as the change is continuous, the derivative acts as an omniscient gauge, measuring the exact momentum of that change at any given microscopic instant.
Wait, I'm going to stop you right there, actually, because you just used a word that feels like a massive trap.
Uh-oh, what word?
Continuous. You said as long as the change is continuous.
I did say that, yeah.
If we can use derivatives to measure the slope of continuous curves, does that mean we can measure literally any unbroken line? Like, if I have a continuous line of stock market prices, can I just find the derivative anywhere simply because the line never breaks?
You would naturally assume so. But that assumption leads us right into one of the most famous pitfalls in calculus.
Really?
Oh, yeah. We really need to dissect this massive misunderstanding regarding continuity versus differentiability.
Okay, let's define the terms then. What does it actually mean for a graph or reality itself to be continuous?
Well, continuity is highly intuitive. It means the physical reality or the line on the graph is completely connected.
Okay.
If you were tracing it with a pencil, you would never have to lift the graphite from the paper.
So no gaps, no sudden teleports from one location to another.
Exactly. Mathematically, it implies that a tiny shift in the input results in only a tiny shift in the output. There are no instantaneous leaps.
That makes sense. Real physical movement is inherently continuous. Like a car accelerating from 0 to 60 miles per hour must physically pass through 30 miles per hour.
Right. It cannot blip out of existence at 20 and reappear at 40.
So continuity is standard physical reality. Now, since we just established that derivatives measure the slope of continuous lines, the logical leap is that if a line is completely connected, I should be able to pick any random coordinate on it and run my microscopic limit calculation to find the slope.
And that logical leap makes perfect sense, but it is mathematically false.
False. Why?
Because differentiability, the ability to find derivative, is a much stricter environment than continuity. To understand why the math rejects the assumption, we have to look at the absolute value trap.
The absolute value trap. Okay, the absolute value function essentially strips away the negative sign from a number.
Yes.
Exactly.
It tells you the pure distance a number is from 0.
Correct. The absolute value of 5 is 5. The absolute value of -5 is also 5.
Okay.
Let's visualize that function on a standard graph. On the right side, where the input numbers are positive, the output matches them perfectly. It forms a straight line pointing up and to the right at a steady 45-degree incline.
So a nice, steady uphill slope. Exactly. But on the left side, where the inputs are negative numbers, the outputs are still forced to be positive.
Oh, right, because it's absolute value.
Right. So the line mirrors the right side. It drops down from the left, descending at a 45-degree angle until it hits 0.
Got it. So the entire graph creates a massive, perfect letter V.
A giant V shape, yes. Now our first diagnostic question. Is the V shape continuous?
Well, definitely. I can draw the entire V, dropping down to 0 and bouncing back up without ever breaking the line. It's perfectly connected.
It is entirely continuous.
Uh,
Now for our second diagnostic question. Can we find the derivative, the exact slope, at the very bottom of the V?
you mean right at the sharp point where the input is exactly 0?
Yes, right at the point.
Well, if the line is unbroken, the point physically exists. The car drove through the bottom of the valley, so to speak. Shouldn't we be able to calculate its momentum?
See, this is where we must remember how the limit actually functions.
Oh, the neighborhood thing.
Exactly. The derivative relies on analyzing the neighborhood around a coordinate. To find the slope at the bottom of the V, we have to look at what trajectory we're approaching as we tighten our orbit around 0.
We shrink the interval.
We check the neighborhood. If we approach that sharp corner from the right side, sliding down the positive numbers, the slope is a constant uphill trajectory. The math reads a positive slope.
Because coming from the right, we are walking uphill.
Yes. Now, approach that exact same microscopic coordinate from the left side, sliding down the negative numbers.
Okay.
The trajectory is entirely different. We are descending. The math reads a negative slope.
Oh, I see. So they crash into each other. The left side is screaming that the trajectory is negative. The right side is screaming that the trajectory is positive. And at the exact coordinate of 0, the math basically has a panic attack.
It absolutely does. It receives contradictory mandates. A derivative requires the neighborhood to agree on the trajectory.
Right.
The limit must be consistent, regardless of the direction of approach. At a sharp corner, the left and right sides are locked in an unresolvable argument.
Because they can't agree, the limit just collapses.
Yes. The derivative fundamentally fails to exist at that sharp point.
So the math gets contradictory information depending on which side of the street it's walking on. Just being an unbroken line isn't enough. The reality has to be smooth.
Smoothness is the exact requirement. If a continuous curve is smooth, the left side and the right side gently transition into one another.
They bend and flex to agree on the trajectory at every single coordinate.
Exactly. The moment you introduce a sharp, jagged corner, the slopes collide and the derivative is destroyed.
Wow. So unbroken definitely does not imply smooth. I mean, I could draw a continuous graph that looks like a chaotic heart monitor full of hundreds of jagged spikes.
You could.
The line would never break, but the derivative would fail at the tip of every single spike.
You've discovered the vital hierarchy of calculus right there. It is an immovable rule. If a function is differentiable, it must be continuous.
Because if I can measure the slope everywhere, there can't be any gaps or teleports. Smoothness inherently requires connection.
Exactly. But, and this is the major pitfall, if a function is continuous, it is not necessarily differentiable.
Okay, I get it now. Continuity is like the bare minimum entry fee. It just means the road exists.
Right.
Differentiability is like a VIP club with a much stricter dress code. The road must exist, and it cannot have any impossible geometric corners.
That is a brilliant way to put it.
Yeah.
And understanding that hierarchy, that mathematical rules have varying levels of strictness and vulnerability is the perfect conceptual primer for where we have to go next.
Oh boy. We are approaching the true final boss, aren't we?
We are.
Because we've spent a lot of time today relying on incredibly visual, poetic language, shrinking the interval, tightening our orbit, microscopic video playback.
It helps build intuition.
It does. We've been using human intuition to guide us around the black holes of arithmetic. But I'm guessing that's not enough for the mathematicians.
No, human intuition is an excellent guide, but it is deeply fallible. Mathematics does not deal in poetic phrases like infinitely close.
It doesn't like poetry.
Not at all. Mathematics demands absolute, undeniable proof. It demands a mechanical blueprint that leaves zero room for misinterpretation or optical illusions.
So we have to transition from the vague to the strict. We have to enter the ultimate game of precision, the Epsilon-Delta Proof.
The Epsilon-Delta logic is the foundational framework that permanently strips the ambiguity away from the word approaching.
It replaces human feelings with an unbreakable algebraic contract.
Exactly.
So how does this contract actually work? I mean, why do we need entirely new Greek letters to prove what our microscopic video playback already intuitively showed us?
We need them to establish a guarantee. The best way to understand the Epsilon-Delta proof is not as a static equation, but as a dynamic structural challenge.
A challenge. Like a game.
Exactly like a game. It's a highly formalized game played between two opposing forces.
Okay, I'm listening.
The game basically states, no matter how strict of an error requirement the universe demands of me, I can design a starting approach that perfectly satisfies it.
Let's break down the players in this game then, who are Epsilon and Delta.
First, we have epsilon, represented by the Greek letter epsilon. Epsilon represents the allowable error on your output.
The allowable error on the output. Got it.
Think of it as a strict manufacturing tolerance. If you claim your limit is approaching the number 6, epsilon is the boundary wall around that 6.
Okay.
It dictates exactly how far your final result is permitted to deviate from the target. If epsilon is 0.1, your output is trapped between 5.9 and 6.1.
So it is the strictness of the demand.
Exactly.
Epsilon is basically the physical size of the bullseye on the dartboard. The smaller the epsilon, the tinier the target you're forced to hit.
That's spot on. Now, the second player is delta, represented by the Greek letter delta. Delta represents the required precision of your input.
The input's allowable range.
Right. Delta dictates how tightly you must control your starting position to guarantee that your final output lands safely inside the epsilon bullseye.
Ah, okay.
If epsilon is the size of the target on the wall, delta is the line on the floor dictating how close you must stand before you throw the dart.
You know, this sounds less like abstract math and more like operating a piece of heavy machinery. Let's try to ground this with a physical analogy.
Let's hear it.
Let's say I'm operating a machine with two dials, an input dial and an output dial.
A perfect visualization. Let's actually use the straightforward equation from our sources for this. Fx equals 2x.
Okay, f of x equals 2x. So the internal gears of my machine simply take whatever number I turn the input dial to and multiply it by 2 on the output dial.
The simplest machine in the factory.
Yeah, and I make a claim. I claim that as I turn the input dial closer and closer to the number 3, the output dial approaches the number 6.
Obviously right. 2 times 3 is 6. The gears demand it.
Obviously holds no weight on the factory floor, though.
Absolutely not. You have to definitively prove that your input dial commands the output dial with absolute certainty, regardless of how strict the quality control inspector becomes.
And the inspector is the opponent in this game.
Yes, and their job is to doubt your machine.
So the opponent plays epsilon.
Yes, and the order of operations in this game is mathematically sacred. The opponent must play first.
They have to set the target first.
Exactly. The opponent walks up to your machine and paints a red error band around the number 6 on the output dial. They declare, I demand your output stays strictly within this red zone.
And that red band is epsilon.
Yes.
And my job is to counter with delta. I have to look at my input dial around the number 3 and paint my own green safe zone.
Correct.
I have to calculate a specific range, delta, so that as long as my input stays inside my green zone, the output is guaranteed to land inside the opponent's red zone.
You must design a counter move to defeat their demand. But notice the strict order here. If you paint your green zone first, if you say, I will keep my input within 1/4 of an inch, the logic collapses.
Well, yeah, because if I commit to 1/4 of an inch first, the opponent can just turn around and paint a microscopic, razor-thin red line on the output dial that my input range completely blows past.
Exactly. Your delta wouldn't be precise enough for their epsilon.
So the opponent dictates the strictness. I merely provide the mathematical guarantee to satisfy it. Epsilon precedes delta.
Always. So let's play the round.
Let's do it.
The opponent paints a red epsilon band of 0.1 around the output target of 6. Your machine multiplies by 2. How do you find your delta?
Okay, I look at the mechanical relationship. Since everything I put in gets doubled by the gears, any error I make on the input dial also gets doubled on the output.
Right.
To ensure I stay within the opponent's 0.1 margin, I have to be twice as strict with my own hands. I just cut their demand in half. My green zone, my delta, is 0.05.
You have constructed the winning counter move. You guarantee that an input within 0.05 of 3 will absolutely result in an output within 0.1 of 6.
And if the inspector gets angry and makes the tolerance even tighter, like if they say the epsilon red zone is now 0.0002.
How do you respond?
I just have it again. My delta becomes 0.0001.
Yes.
It literally doesn't matter how microscopic they make the red zone. I have a universal verifiable mechanism dividing their demand by 2 that guarantees I can find the required green zone.
That's it.
I'm working backward from their demanded tolerance to prove my total control over the system.
And that mechanism, that ability to always generate a functional delta from any given epsilon, is the proof. You have rigorously proven the limit.
Wow.
You didn't rely on the vague poetry of infinitely small. You didn't wave your hands. You provided an airtight algebraic contract that links the precision of the cause to the accuracy of the effect.
That structural revelation is incredible. I mean, while the gears of the machine obviously get way more complex if we're dealing with, like, parabolas or trigonometry instead of a simple multiplier, the game structure remains completely identical.
Entirely identical. You just find the algebraic link that allows you to translate the opponent's output demand into your input requirement.
It is elegant, it is rigorous, and it is the bedrock upon which all modern calculus rests.
It really is.
So we have climbed the final staircase, we navigated the arithmetic black holes, we used limits to calculate instantaneous momentum, analyzed the trap of sharp corners, and built the airtight Epsilon-Delta machine to prove it all works.
We covered a lot of ground.
We did. But this brings us to the ultimate question for you listening, the real-world payoff.
Yes, why subject ourselves to these rigorous mathematical contracts in the first place?
Exactly. Math without physical application is just an isolated puzzle. Why do engineers and scientists rely on these specific tools? What is the tangible payoff of this knowledge?
The payoff is nothing less than the operational capacity of the modern world.
That's quite a statement.
It's true. Limits, derivatives, and the Epsilon-Delta proofs are the fundamental underlying mechanisms that allow us to predict continuous physical phenomena without our models collapsing. Without these tools, we cannot engineer a world that moves.
Let's dissect the specific applications from our sources then. Let's start with artificial intelligence. Our sources specifically mention AI and a process called gradient descent. How does a purely digital brain utilize the mathematics of continuous change?
Gradient descent is the literal engine of machine learning. Imagine an AI attempting to learn a highly complex task, like translating human speech or recognizing a face.
Okay.
In its initial state, it is terrible at the task. It produces massive errors.
It's essentially just guessing.
Basically, yes.
Yeah.
You can visualize the magnitude of those errors as a vast, dark, multidimensional landscape, a topographical map of hills and valleys.
Oh, I'm picturing it.
The higher the elevation on a hill, the larger the AI's error rate. The bottom of the deepest valley represents the point of minimum error. That valley floor is where the AI is perfectly trained and highly accurate.
So the AI wants to get to the bottom of the valley, but it's operating in the dark. It doesn't have a bird's eye view of the landscape.
Exactly. It only knows its exact current coordinates.
It is dropped onto the slope, blindfolded. How does it find the absolute bottom? It has to physically feel the ground beneath its feet to determine which direction is sloping downward.
And how does it do that? It calculates the slope.
It calculates the derivative.
Yes. It uses the mathematics of instantaneous change to measure the exact steepness and trajectory of the ground at its specific microscopic coordinate.
So the derivative acts as a mathematical compass, pointing out the trajectory of the steepest downhill path.
Precisely.
So the AI calculates the derivative, takes a tiny step down the slope, stops, and calculates the derivative again. It constantly interrogates the slope of the curve to adjust its internal parameters, inching closer to the minimum error.
And how does it know when it has finished learning?
Well, it hits a flat spot. If it reaches the bottom of the valley, the ground levels out. The slope becomes zero.
And the derivative is zero.
Exactly.
Oh.
Without the derivative acting as a directional gravity compass, the AI is just wandering in the dark, guessing blindly. Calculus provides the navigational architecture for machine learning to optimize itself.
And it doesn't stop there.
Huh.
The sources also mention technology processing image signals. And this circles back beautifully to our absolute value trap.
The pitfall of smoothness.
Yes, it is a stunning real-world application of non-differentiability. When a software program, like a facial recognition algorithm or an autofocus lens on a camera, analyzes a photograph, it is processing a continuous stream of pixel intensity data.
Right.
How does the software mathematically determine where a person's face ends and the background wall begins?
It has to look for a visual boundary, an edge.
And mathematically, a visual edge is a sudden, drastic change in pixel contrast. It is a sharp corner in the data stream.
Oh, I see where this is going.
The software runs a derivative calculation horizontally across the pixels of the image. Where the image is smooth, like the gentle lighting gradient across a person's cheek, the pixels transition smoothly.
The derivative calculates a consistent slope without issue.
But then the calculation reaches the edge of the jawline, set against a dark background.
The slope of pixel intensity coming from the left crashes violently into the slope coming from the right. It forms the sharp point of a V-shape.
The visual data is continuous, but it is no longer smooth.
The mathematical panning attack. The left and right slopes completely disagree, and the derivative fails to exist at that specific pixel.
Exactly. And the software detects that mathematical failure. It flags the non-differentiable point.
So by scanning the entire image and connecting all the coordinates where the derivative mathematically crashes, the software effectively draws an exact outline of the face.
Yes. The failure of the derivative is the precise mechanism used to detect edges in digital imagery.
That is absolutely phenomenal. We use the moments where the math breaks down to map the boundaries of our visual reality.
It's beautiful, isn't it?
It really is. What about physical engineering?
Oh, the entirety of classical mechanics relies on derivatives to manage stress and force. When aerospace engineers design a rocket trajectory, they aren't dealing with static weights.
Right. As the rocket burns fuel, its mass constantly decreases.
And as it rises through the atmosphere, air resistance and gravitational pull constantly mutate.
Every single variable is a shifting curve.
You cannot calculate orbital insertion using average speeds over massive distances. The calculus of instantaneous change is required to constantly update the thrust parameters second by microscopic second.
That makes total sense.
Similarly, when civil engineers design a suspension bridge, they have to manage continuous vibrations from wind and traffic. The materials must flex and react to changing pressures.
They have to know the exact slope of the stress curves to ensure the steel doesn't reach a failure point.
Exactly. To build a world that moves, you must fluently speak the language of continuous change.
Synthesizing this entire journey. Limits are the ingenious workaround that allow us to increase observational precision forever without hitting the zero crash wall of arithmetic.
Beautifully summarized.
Derivatives take that limit concept and apply it to motion, becoming our universal speedometer for reality. We learn that reality must be smooth, not just unbroken, for those measurements to work.
And the VIP club of differentiability.
Right. And the Epsilon-Delta game is the ironclad mathematical contract, the structural blueprint that proves all of it operates with absolute certainty.
These concepts are not simply academic hurdles designed to torture university freshmen.
Though it feels like it sometimes.
It does. But they are the translated mechanics of the physical universe. They are the tools that allow us to take the muddy, constantly moving chaos of our world and process it into a language of strict prediction.
For you listening, thank you for taking this deep dive into the architecture of motion with us today. We waded into the mathematical muddy waters, and we emerged with a blueprint for reality.
We did.
We discovered that the intimidating final bosses of calculus are actually just a highly sincere, deeply rigorous way of answering the simplest human question. Exactly how close is close?
It is a remarkable testament to human ingenuity. We took a vague, everyday feeling of discomfort and engineered it into the mathematical engine of the modern scientific era.
And it leaves me with a final thought for you to mull over as we end. Today we explored how mathematics uses the strict rules of the Epsilon-Delta game to completely eliminate ambiguity from the concept of getting closer.
It took a flawed human feeling and forced it into an absolute verifiable rule.
It really makes you wonder, what other vague, ambiguous feelings or social frictions in our everyday human lives could be perfectly resolved if only we knew how to define the mathematical rules of the game?